Here we have the sample space of the outcomes for the rolls of 2 fair dice. We can see that we have 6 by 6 equals 36 outcomes. We can get the number of outcomes by considering the fundamental principle of counting. There are 6 ways that the first die can appear after it is rolled, and for each of these 6 ways we have 6 ways for the second die to appear. So by the fundamental principle of counting, we have 6 by 6 equals 36 ways for 2 dice to appear. So if we want to write out the sample space, we could assume that the first one appears on the first die, and if 1 appears on the first die, consider all the outcomes. Well, we have 1 1, 1 2, 1 3, 1 4, 1 5 and 1 6. Then we can consider the case where 2 appears on the first die, and we can list the possible outcomes for when 2 appears on the first die, and so on for 3, 4, 5 and 6 until we've covered all 36 outcomes. Now these outcomes are equally likely because we're dealing with 2 unbiased dice, so there's no reason to suppose that any one of these outcomes is any more or less likely than the others. And the roll of each die is independent of the other die. So the result for the first die has no effect on the result for the second die. So the probability of getting a 1 on the second die is 1/6, regardless of what appears on the first die. Similarly, the probability of getting a 2 on the second die is 1/6, regardless of what appeared on the first die, and so on. The probability of getting any number on either die is 1/6. What is the probability of getting 2 6s? Well, we go to the sample space and we look for the event that consists of outcomes which have 2 6s in them. And we can see that that event just has one element. It's this element here. So we put 1 over the total number of elements as we've seen before. So the answer is 1/36. What is the probability of getting 2 odd numbers? Well, we just have to count up the outcomes that have just contain odd numbers. So the event which has outcomes just consisting of odd numbers has 6 elements in it. So this event consisting of 6 elements is a subset of S. To get its probability, we put the number of elements in it, which is 6, or sorry, not 6, but 9, over the total number of elements, which is 36. This breaks down to 1/4. So 1/4 of all the outcomes are outcomes consisting of just odd numbers. Next, we want the probability of getting at least 1 6. Well, we can see that all these outcomes have at least 1 6 in them, and all of these outcomes here have at least 1 6 in them. So we just count the number of outcomes that consist of at least 1 6, and we put that number over the total number of outcomes. So we see we have 1 2 3 4 5 6 7 8 9 10 11. So the answer is 11/36. We could arrive at this probability by considering these two sets. This set here represents the event that the first die shows a 6, and this set here represents the event that the second die shows a 6. So we want the probability of this event or this event here. Let's just call this event E1 and this one E2. So just to remind you of set notation, we want the probability of E1 or E2. So we want the probability of this event or this event. And in that situation, an outcome will consist of at least 1 6. At least 1 6 means exactly 1 6 or 2 6s. This outcome is allowed. So we know that in set notation, this is the probability of the union of these two sets, and we know that this is the probability of E1 plus the probability of E2 minus the probability of the intersection of E1 and E2. You can see it's just much easier to count the required outcomes from the sample space. But anyway, I want to go through this. The probability of event E1 is the number of elements in E1, which is 6, over the total number of elements in the sample space, which is 36. Event E2, probability of event E2 is the number of elements in E2, which is 6. We put this over the total, 36. And what about the intersection? How many elements are in the intersection of these two events? Well, we can see that we just have one element in the intersection. So we get 6 and 6 is 12 minus 1 is 11 over 36. An important point here is that E1 and E2 are independent events. So that means that the probability of getting event E2, that is a 6 on the second die, does not depend on the probability of getting a 6 on the first die. If event E2 has occurred, it means that one of these outcomes has occurred, and the occurrence of E2 does not depend on E1 having occurred. So the probability of E2 occurring doesn't depend on E1 having occurred. The probability of E2 is still going to be 12 over 36, or sorry, 6 over 36. This probability here is not going to be affected by E1 having occurred. Obviously, the two dice are independent of each other. The dice are not connected in any way. As we saw in a previous video, if two events E1 and E2 are independent, then the probability of E1 intersecting E2, or we could think of this as the AND operator, the probability of E1 and E2, that is the probability of getting a 6 on the first die and a 6 on the second die, is got by multiplying the probabilities together. The probability of getting a 6 on the first die, that's E1, is, as you can see, 6 over 36. The probability of E2 is also 6 over 36. There's 6 outcomes, 6 elements in the set E2, and if we multiply these together, this is just 1/6 times 1/6, which is 1 over 36. So it makes sense to multiply the probabilities to get a much smaller probability, 1 over 36. So if we want the probability of one event and another event, we certainly don't add the probabilities, because if we were to add these together, 1/6 plus 1/6 leads to a bigger probability of 2/6, which would make no sense. It should be easy to see that the probability of getting a 6 on the first die and a 6 on the second die should be less than the probability of getting a 6 on just one die. Getting 6 on both dies is less likely. It's much less probable. So by multiplying the probabilities, we get a smaller probability than either of these two probabilities. Something that I should mention is that events E1 and E2 are not mutually exclusive events. We can see that if we get a 6 on the first die, it means that E1 has occurred. If we get a 6 on the second die, it means that event E2 has occurred. But you can see that both events can occur. So if E1 occurs, then E2 can also occur. If 6/6 appears, then E1 has occurred and E2 has also occurred. So these two events do not exclude each other. They are not mutually exclusive. In part D, we want the probability of getting at least 1/6 or two even numbers. Well, we've already highlighted the event getting at least 1/6. Let's do it again. I will call it E1. So E1 consists of 6 and 5, 11 elements. Now what about two even numbers? Let's see that in a different color. Well, here is an outcome of two even numbers. I will call the event consisting of the outcome consisting of two even numbers E2. So I can't circle E2 because these values are separated from each other. I'd have to put 2, 2, 2, 4, 4, 2 and 4, 4 together, and then I could circle them off. I'm not going to bother doing that. So basically all we have to do is just get the union of the two sets, because we have an OR situation. So the union just means count the elements in both sets. Of course, we don't count elements twice. We only count an element once. So you can see here we have 11 elements inside E1, and we don't count the ones in blue twice. We have 11 plus 4 elements out here. 11 plus 4 is 15. So the answer is 15 over 36. Of course, we can use our set notation and use this statement again here like we used it before, and I proved this several videos ago. So we want the probability of E1 or E2. That's the union of the two sets E1 and E2, and the probability of that union is the probability of E1, which we saw before is 11 over 36. There are 11 elements in E1, plus the probability of E2, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 elements in E2, so we put 9 over the number of elements in the sample space, and we subtract off the probability of the intersection of E1 and E2. So we count the elements in the intersection: 1, 2, 3, 4, 5. So again, we get 11 and 9 is 20 minus 5. We get 15 over 36. Here we notice that events E1 and E2 are not independent, because if we multiply the probability of E1 by the probability of E2, we have 11 over 36 times 9 over 36, which is not equal to 5 over 36. We saw that the probability of E1 and E2 was 5 over 36. We just looked at the intersection of the two events. So there are 5 elements in the intersection, these 5 elements highlighted in blue. So that means that E2 must depend on E1 and vice versa. E2 is the event getting even numbers on both dice. Well, it does depend on E1, because both numbers could have been 6s, or we could have had a 6 and a 4. Suppose that event E1 has occurred. That means that at least one 6 appears on the two die. Well, that does affect the probability of there being two even numbers on the die. It does affect the probability of E2, knowing that E1 has occurred. Because if E1 has occurred, then it could mean that 6-2 has occurred, or 6-4, or 6-6, or 4-6, or 2-6. Anyway, I'll discuss more about conditional probability later, but for now I just want to state that E1 and E2 are not independent, because the product of these probabilities is not equal to the intersection. So PE1 times PE2 is not equal to the probability of E1 and E2. I might also say that E1 and E2 are not mutually exclusive, because the sets E1 and E2 intersect. They're not disjoint sets. We have points of intersection of the two sets. So the two sets overlap, but of course it doesn't necessarily mean that they're independent. Just because two sets overlap, two events overlap, they could still be dependent. They could actually be independent, as we saw in a previous question, as we saw in part C actually, we had two overlapping events, yet the events were independent. So we have to be careful here. We're not looking at, we don't look at the intersection. It's only for to test to see if sets are mutually exclusive that we look at the intersection, see if there's an intersection or not, see if the sets are disjoint or not. But for independence, we have to do this calculation here, PE1 times PE2, and then compare it to this number here. That's the only way we can tell. Finally, we want to get the probability of getting numbers whose sum is 8. So let's see now, 5 and 3 is 8, but by symmetry 3 and 5 is also 8. 6 and 2 is 8, of course, and if we look along this diagonal here, we have 2 and 6. What else is there? We have 4 and 4 actually. And that's it. Numbers above this diagonal sum to a value that's less than 8, and numbers below the diagonal sum to a value that's more than 8. So we have 1, 2, 3, 4, 5 elements in this set. So we have 5 over 36.